All right, I'm rolling.
Good morning, everyone. My name is Harry Zhang, and I work as a software development engineer at Applatix. I work for the platform team, and my job is to make sure that Kubernetes is up and stable and good for us, and all our workflows are executed correctly. And here is my colleague, Abhinav.
Hi, I'm Abhinav. Thanks, Harry, for letting me talk. He's actually the Kubernetes expert, and so he's going to deep dive a lot into what it is to make Kubernetes production ready. Along with him, I work in the platform team on some aspects of Kubernetes, but I also focus a lot on sort of our overall system design. And so what I'll focus on a little bit is basically how do we use Kubernetes, and what do we define as production ready? Like what are the aspects of our system that sort of determine what Kubernetes is to us? So actually, a very short marketing pitch over here. This is not a marketing presentation, so it's a technical talk. So the only thing I want to say about Applatix is that this is a platform that is built to run containerized applications in the cloud. And this, so our platform is actually built completely on top of Kubernetes. So Applatix is basically an application that runs on top of Kubernetes. And what is our goal? Our goal is to simplify your journey to the cloud with infrastructure automation, end-to-end DevOps workflows, and monitoring, audit, and governance. All right. So the outline of the talk kind of goes in sort of as a story of what we actually went through when we used Kubernetes. So when we started using Kubernetes, we were just like, hey, let's fire up this Kubernetes cluster, let's get things going, and things were looking good, and then we started hitting a lot of problems. So we started to understand what are those characteristics of those problems, how did we define what was production ready for us. Harry's going to talk about sort of a little bit of a design overview of Kubernetes for folks who are not familiar with that. And then we'll obviously dive into two main aspects of Kubernetes, the master and the minion, and how we harden each one of them. All right, so let's go into what is production ready. Okay, so again, a little bit of overview about what Applatix does. It's basically a workflow engine that runs on top of Kubernetes. So a workflow engine allows the user of Applatix to define a workflow which is composed of tasks. Each task is actually a Docker container, and because it's on Kubernetes, this container runs as part of a pod. The user can define any sort of workflow. Over here on the bottom right of your screen, we are showing a part of our Applatix continuous integration workflow. And you can kind of maybe very vaguely see that there's a checkout followed by a bunch of tests that are happening, and followed by a whole bunch of, those are actually unit tests, and followed by a bunch of builds. And actually one of the build failed over here, so you can actually see the red over there.
Yeah, this is our daily task. Sometimes it fails, and sometimes everything is successful, but we want to make sure that our product is fine and ready to ship to our customers.
Right. You can kind of obviously see over here that there are some tasks which can be run in parallel and some which are run in serial, one after the other. And so the number of tasks that actually run on the system in parallel is defined by the kind of workflows that you've written as a user, and the number of workflows that you're executing simultaneously. To just give a quick example of a very simplistic example.
I like this example.
It's like, you can assume that this workflow that you see at the top is like your build, test, approval, and deploy workflow. And workflow 1 and workflow 2 kind of are identical because you may have multiple users submitting the same workflow. But if they are skewed in time, in this overly simplistic example, you can see that there are 3 pods where each of those circles represents a pod or a task in our workflow. There are 3 pods that are running in parallel. And so that would sort of define the max load on the system. Whereas if they are completely aligned in time, then 4 of them are running in parallel. And obviously in this totally contrived, made up example, everything is perfectly aligned, and that's not the case in the real world.
Right. To help you guys better understand, in the first graph, in the time slot 1 to time slot 2, we have 1 pod tiered down and the 3 pods coming up. So we have 4 pod modifications at the same time. But for the second graph, from step 1 to step 2, we have 2 pods tiered down and 4 pods bringing up, which is 6 pods modifications at the same time. So the workload at that moment for the second graph is higher than the first one.
Great point. All right, and actually that sort of brings us into sort of how these workflows are created. So on Applatix, these workflows can be created based on policy triggers. So you could actually write a policy is like a cron job basically,
Yes.
right? And so so you're writing this specification that says, hey, I want my workflow to run every minute or every hour or whatever your requirements are. And they could also be event triggered. So if Harry decides to check in a big change to Kubernetes configuration or something like that, that's actually going to trigger another workflow as well. So,
Right.
And the other thing that happens is that our system is actually sort of a mix of workloads. So there are pods which are born and die because they are part of this workflow which does this unit amount of work. And then there are other pods which are part of deployments, and deployments are like your microservices which are long running. And so you have a mix of pods, right? Some which are short running and some which are really long running. So we are now coming to sort of the how we are defining what stability is for our system.
Right.
And what we find for us is that this pod churn or the notion of pods getting created and deleted in unit time is sort of what defines our stability. Right?
Exactly.
And so the production ready cluster basically needs to be stable in the presence of this kind of pod churn.
Yes, exactly. Especially we're pressuring our cluster with very high pod churns to make sure that our cluster can be suitable for any kind of arbitrary customer workload. So our current Applatix production workload consists of a cluster of 30 M3.2 extra large nodes. That is equivalent to 240 CPU cores and 1 terabytes of memory cluster-wide. And we do run a mix of short and long-running pods. We have CIs, we have deployments as well. And during the very peak hours, we can have about 2,000 pods coming up and down every minute, and which is equivalent to about 8,000 containers.
Oh, that is a lot of pods going up and down. Now I can see why Harry lost so much hair when he joined.
We were pressing Kubernetes almost to extreme.
But a quick question over for you. So you mentioned that the 30 M32X large node cluster is our production cluster. Is that the only cluster we support?
Good question. The 30 M3.2X large node cluster actually is our largest configuration for now, and this type of cluster is suitable for a middle-sized company and to deploy some real production workload. But if you have a smaller team, or if you just want to get a sense of what Applatix experience is, we do have smaller clusters which are more economic options.
So in your scaling experiment, I presume this is the sort of the top of the line, and then we are doing whatever is required to scale our infrastructure down for the more economical choices.
Yes, this is actually one of our most important benchmarks we're having.
Awesome.
So before we go into details about Kubernetes, I'm going to give you guys a heads up of the design of Kubernetes and just some background information. So Kubernetes, you can see it consists of a Kubernetes master and a couple of Kubernetes minions. On the master, there are a couple of core Kubernetes components running, such as API servers, etcd, controller managers, scheduler, and kubelet and kubeproxy. And on minions, there are Kubernetes workers, which is kubelet and kubeproxy running. So I'll give you guys an example. So imagine you're creating a pod. First, you have a post API calling into the API server with a pod spec. And then, because every Kubernetes components talk with Kubernetes API server, and then that pod will be propagated to the scheduler, because it's a new pod, it needs to be scheduled. So the scheduler will run its scheduling algorithms and to decide on which node this pod should run. And then the scheduler will do a patch operations to the API server to write into the pod spec, and this is the node you should run. And then this pod gets propagated to the kubelet running on that designated node. And after kubelet receives the pod, it will continue to manage the pod's lifecycle according to its spec. So you can see that even if there's a single pod creations, there are a lot of components getting involved, and there are a lot of events generated. For example, the scheduler, when it's started to evaluating nodes, it generates events. When kubelet started to pull container images or started to run containers, also there are multiple events generated.
I see. So one quick question over here is that I noticed there is this kube controller manager, and you mentioned that there are 20 plus controllers.
Sure.
Are they related somehow? Or what's happening over
Sure,
there?
yeah, good question. So Kube Controller Manager is a big application that contains the control logic of multiple Kubernetes objects. So for example, they have a controller for deployment, they have a controller for job, they have a controller for daemon set, stateful set, services, and all kinds of Kubernetes objects. It's a big application, it's contained with small applications to make sure that all Kubernetes objects will run exactly and correctly according to their specs.
I see.
So for Kubernetes cluster, we started with running the cluster with all default values.
Okay.
But what we see is that with default values, you can run a hello world example, but it's definitely not work for us in our production. There are a lot of things can go wrong. Actually, anything can go wrong. So let's start with master where most of the problems happens. The first thing we're gonna see is that master can crash when the cluster is having high loads. Basically, everything can crash on master. When we're having really high loads, what we first see is that the master node will have very high CPU and memory utilizations, which means Kubernetes is very busy on that. And for the problems, we have two extremes. On the one extreme, we see out of memory killing on multiple core Kubernetes components like API server, etcd, scheduler, controller manager, everything.
Okay.
And on the other extreme, we can see that some of our API calls can take a very long time to return. So these are the two extremes we're having. Or sometimes the API calls can return, but actually the objects we created will take a long time to respond, to start processing. So that makes us to go to see like what kind of knobs can we turn to make things right. So we started with API server because this is the heart and the center of Kubernetes. Okay. These are the two flags we found on the API server that can help us to make things right. The first one is called control the maximum request in flight, which is throttle the API request to be processed in parallel. The second one is the API server used that to configure some of its caches. So it is a target RAM megabytes it should use. We started with default values, of course, but if we see if there's too many kills, we try to reduce these two values. If we see there's a performance issues, we increase these values. The rule of thumb we discovered while experimenting with Kubernetes that we use one in-flight request per 2-pod cluster-wide for maximum request in-flight. And we use about 2.5 megabytes of cache sizes per pod. But these are just a rule of thumb that we configured for our workload. This might or might not work for yours, but this is definitely a good point to start with.
Okay. I guess I can see how both of them are correlated to increasing memory. So I'm assuming that we scaled them up for our production cluster, the 30-node cluster.
Exactly.
And scaled them down for our economical clusters.
Yes, exactly. That's exactly what we're doing. So let's go to the controller manager. So the controller manager provides us with more fine-grained ways of tuning of controlling the concurrency of that. So more concurrency means there are more workers to process a single type of objects every time. We started with default value again, and we increase the value if we see there are more spare resources on master, or for the components we use more frequently. So for examples, we support deployment, so we use a lot of deployments, replica set, and so on. So we use 20 workers for a concurrent deployment sync, concurrent replica set sync, and concurrent replication controller syncs. And we also decrease the value for some components we don't use that frequently.
What would happen if, let's say I get these values wrong? So let's say I put lowball values over there.
Yes.
So
if you set the value to too low, it is much safer than you're setting the values too high, because if you're setting the value too low, the worst thing you can get is that there are so few workers trying to process the same object at the same time. So for example, you create a deployment, you might see there's a noticeable delay before the deployment start processing, and Kubernetes is creating pods for that, and Kubernetes is pulling images for that. Because there are so few workers inside the controller manager, then they are still busy processing some early created deployments.
Makes sense.
But if you make the number too big, then it will take too much CPUs or too much memories, and the master node will get confused and they're going to start killing things, or some performance is going to be throttled. That's worse than under provisioning of that. That's our experiences.
Makes sense.
Right. So for Controller Manager prior to Kubernetes version 1.6, they also provided 3 flags to configure the cache sizes. You can configure the daemon set, lookup cache sizes, replica set, lookup cache sizes, and replication controller lookup cache sizes. We use 4 gig, and 1 gig for them respectively on our production cluster, and we set it to small numbers in our small clusters. But for Kubernetes version after 1.6, they re-implemented their entire cache infrastructure, so these 3 flags no longer apply.
Right. Yeah, I guess Kubernetes is also a work in progress, so some of the things have changed over time.
Exactly.
And that also is something that one should keep in mind.
Yes, exactly. They are continuously improving their design and their implementations to make their system more efficient. Okay, so this is also important. Since we already set the maximum in-flight request inside the API server, we should also throttle the API from the client side. So Kubernetes provides this set of flags to configure in multiple Kubernetes components, including their official add-ons. You can see these 2 sets of flags in kubelet, in Controller Manager, in Scheduler, in kubeproxy, and a bunch of add-ons. The default values are generally good for us, except we tune the number for the scheduler, because we believe if it is a busy cluster, we have a lot of pods to schedule. It is fair enough that the scheduler can make more API calls because we want our pods to be scheduled in time. And so the rule of thumb is 3 QPS, which is query per second, per 10 pod for the scheduler, and the number is doubled for the burst value. And again, this is heuristics for our workload, and you guys can start from there, but you can tune according to the workload you guys are using.
All right, so I guess another thing that we did was we sort of took another hard look at how we are using the Kubernetes cluster, and like I said, Applatix is an application that runs on Kubernetes, yes. Right? So we are ourselves using aspects of Kubernetes such as the API server. One of the things that we noticed was that if pods are created and they are sort of lying around without getting scheduled, for example, then we notice that there is more problems that we see on the master. Yeah. And so we have an admission controller which basically manages the total resources of the cluster. Mm-hmm. And so when a task is created, right. And the task is basically converted into a pod, mm-hmm. The admission controller pretty much guarantees that the pod would start soon enough, yes. So that it does not remain pending for too long. So that sort of helps Kubernetes be a little more stable.
So what can go wrong with it? There are a lot of pending pods there in the cluster.
Okay, yeah. So actually, that's kind of what happened in the beginning when we started working with this.
Exactly.
So we threw the kitchen sink at it, right? And we had a lot of pending pods. And what we noticed, as an example, mm-hmm. was that the scheduler would try picking them up and trying to schedule them all the time. And every single time the scheduler picked it up and tried to schedule it, mm-hmm. That was activity that was done that had to go through the API server, and yes. that had so all those components which you just talked about, mm-hmm. were sort of getting involved over there.
Exactly, and there are multiple events generated for each pod's scheduling as well. So imagine if you have 1,000, 2,000 pods pending there, the scheduler is going to run all of them and to create a lot of events, and all these events will go through the API server, and if there's other services that is interested in this event will also go to all these other services. So the system workload will be added up to a very large degree.
Yeah, in fact, what was also happening was because like you said, the events were going into the API server, and they all also get stored in etcd.
Exactly.
So we noticed etcd's performance was also starting to tank, right?
And because there are so many events, Kubernetes is also busy doing those cache evict and cache refresh and things like that. So it's definitely not a good practice if you have a lot of things pending inside a production cluster. You want to make sure you want to throttle the objects you're creating, so that will make the cluster more stable and can handle more workload.
Makes sense. So again, like I said, we were using Applatix. Applatix was using Kubernetes as well. Sorry. So what we have is basically, when you write a Docker container, and this Docker container is your your command that is doing your build, for example. We also have a sidecar container, which is like this Kubernetes construct, which is a container that runs inside the same pod, along with the main container. And our sidecar container is sort of what we call our infrastructure container, and that infrastructure container is communicating with Applatix infrastructure to give information about what's happening with the main container, right? Yeah. So is the main container done? And do we collect artifacts? We have this notion of artifacts that could be generated by a container, and so those are basically files and file objects that need to be extracted out of the container and then passed along to other steps.
Right.
So all this is actually done by the sidecar container. And one basic thing that we were doing early on was naively checking to see if the main Docker container was complete or not. And so we would talk to the API server and we would say, hey, I am this pod. Tell me what is the status of all my containers. And then we would go and say, let's see what's the status of the main container. And we would do that every so often. And that adds load to the API server.
Exactly, that's a lot of load.
Right, and actually we saw that was a lot of load. That scaled up very quickly to really hurting the API server. Now it turns out that kubelet, so kubelet is the component which is sort of responsible for bringing up and running this pod on a minion node, right, on a worker node. And so kubelet has this undocumented API called /pods. I think it's like at 10255 port or something.
Yeah, this is the default port, the read-only port kubelet is opening.
Right. So you can actually get the pod information from there, and so we actually decided to very quickly switch to that, and that also helped tremendously save API server bandwidth.
Exactly, and since kubelet is responsible for managing the lifecycle of the pod, actually kubelet can be the source of truth of the status of that pod. So if we switch to get the pod status from kubelet, we even get more up-to-date information.
Right, we technically could get the same information faster from kubelet than we would if we had to go all the way to the API server and then back again. Apart from increasing the amount of load we would have.
Exactly, you're right. Okay, so after talking about the masters, we should go to the minions. Minions can be marked as unhealthy under a lot of conditions. Again, the same as master, everything can go wrong on minion, which is really a pain for us when we realized this problem, and we really did a lot of things to harden minions. So for example, Docker can stuck a minion. Kernel on the minion can crash. In the early version of Kubernetes, there's a kubelet bug that it can leak pod IP. So once for a while, after it leaks out all the allocable pod IPs, this node is basically cannot run any pod anymore. And in other rare cases where kubelet crashes, there are sometimes when systemd refuse to restart kubelet. So which means this node, there's no Kubernetes worker on this node. So this node basically is useless. To address these problems and to get to not get into these problems, we implement 3 layers of protections in our minion. Protection layer 1, we try to not to have ourselves get into the problem in the first place. The first thing we did is we limit the number of pod per node. This is to control the workload of kubelet and the workload of Docker. We use 80 pods per M3.2x large node and with smaller numbers for smaller node. And you can do that by using the --max-pods flag for kubelet. The second thing is that to avoid a kernel scheduling bug in Linux kernel, we also removed all the CPU limits on that. Abhinav has more detail on that.
So this was actually a little bit of an interesting problem. So what you see over here is basically a kernel stack dump, right? And if you can make out, it starts off with a null pointer dereference. And then if you look at the stack trace, what you find is that it's the scheduler code that is getting involved over here. So now what was happening was very interesting. So when we asked the user to express their task as a Docker container, we also asked them what CPU and how much CPU and memory you're going to use. And so we would take that information and pass that along to Kubernetes pod spec. And in Kubernetes pod spec, you can basically describe CPU in 2 ways, right? So you can say what is the request and what is the limit of the CPU. Now the request works in the sense is basically passed to the CFS or the fair share scheduler in the manner that let's say that you have just one job running, right? So there's just one process running, and you have one CPU, and you have said I need half a CPU for this job. So even though you just said you need half a CPU because it was passed as the request part of it, the job could potentially use the whole CPU because there's nothing else that's running. But if you use the limit aspect of it, then even if there are no other jobs running, the scheduler is going to restrict you to using no more than 50% of the CPU in this example where we said that we're going to use half a CPU and the total number of CPUs was 1. So what we did was we actually, at some point of time, we enabled passing what was specified in the workflow specification as the CPU request and limit. And it turns out that we started seeing a lot of minions crashing after that. And it was very interesting because we were like, why are all these minions crashing all of a sudden?
Yeah.
And it was kind of random. It was what we observed actually was the more the load was increased on the minion, the more frequently it crashed.
Right.
And we started looking at the stack traces, and it turns out that there is apparently some bug in the kernel scheduler code which is getting exposed when the limit value is set. So our workaround obviously right now at this point of time was to not pass the limit. And that's not too bad because the CPU as compared to the memory limit is not as I guess dangerous, right? So when you pass it in the request, you're already using the fair share scheduler. So for example, if you have 2 tasks, both of them requiring half a CPU, that are running on this like one CPU node, they would be allocated half a CPU each. So it's only the case when you are over provisioning your node and underutilizing your resources is when a job could eat up more resources than it asked for.
Exactly.
And that's not a bad case.
Right, and that actually increased the total resource utilization on the same node if you are over provisioning yourself, and the additional quota can also be moved to some other processes that running on that node. So the CPU don't get any spare time. You can keep the CPU busy.
Right.
I have a question on this. Does other people in the Kubernetes community also have the same problem?
Yeah, I believe this was actually reported to GitHub as well. They have, there is an open issue for this. We have posted our stuff over there as well.
Okay.
And we continue to keep track of it. At this point of time, we just feel that it's not. It's a problem you should be aware of. Like if you start hitting these problems, take your limits out of your pod specifications. But I don't feel at this point of time it is like sort of a mission critical problem for us.
Right, and we don't see any kernel crashes after that, right?
Oh yeah, absolutely. The kernel crashes just disappeared after that. So.
All right, got it. All right, okay, protection layer 2. Once there are things going wrong, we try to fix the things locally. We implemented 2 health checks running under system D. The first one is Docker health check. We periodically check Docker PS and see if Docker can potentially stuck. We restart, or Docker is not even running, Docker crashed for some reason, so on and so forth. And we restart Docker when necessary. But on really bad node, when we keep on restarting Docker but failed, then we terminate the node. That can be possibly because there is something even worse happening than Docker. For example, the Docker graph storage can crash, or some other things can go wrong. There's a runaway processes on the node that is constantly spawning other processes. Anything can happen, so we just terminate the node.
Right, and we also had the like you mentioned, the allocatable IPs being full. That's another issue where.
Yes, exactly. So that part we try to get around with it with a kubelet health check. So kubelet health check does 2 things. One is to check the kubelet we're using. Does it hit the bug to leak out all the allocable IPs? If that be the case, since this node is already useless, we terminate the node. Or if there's other cases there, kubelet systemd refused to restart kubelet when it crashed, we manually restart kubelet, not manually, but by the kubelet health check. So it's another daemon going through and try to make things right. But for the allocable IP leak bugs, the community has already fixed it in some later versions. So if you're using Kubernetes later than 1.5, I think you're good with that.
I see. So some of these checks, are they being done by Kubernetes themselves as well? Or are we adding to them? Or
Good question. So I do realize that in the later version of Kubelet, the Kubernetes community has already implemented a Docker health check. And so if the Docker is not responding or the Docker API is stuck, actually Kubelet will restart Docker. But Kubelet won't terminate the node because its job is to run on the node to work with containers. But since we realized that sometimes a node can really go bad, even if Docker fails to restart, then we really need to intervene in something. So I think this kind of Docker health check still has its own value.
I see.
And also, since Kubelet is checking Docker, we don't have anything to check Kubelet. Then I think the Kubelet health check, we still need to put some monitoring processes on there just in case things goes wrong. And this also harden our node in our production, and it really helps. We do see actual cases, and these two health checks are really restarting the components, and things goes back correctly again.
Okay.
Protection layer 3. So this is a more, we implemented a service called Minion Manager that runs inside the Kubernetes. This is a microservice that and it is monitoring the minions from a Kubernetes perspective. So there are two cases that this service will think the minion can go wrong, the minion is not good. The first one is the minion is marked as not healthy by Kubernetes. Kubernetes has a node controller running inside the master and receiving heartbeats from the minion. If the kubelet is down or Docker is down or anything goes wrong, it will mark the node as not healthy. So if the node stays in not healthy state for a long time, we terminate the node because we know the node is wrong and our local fix doesn't work.
That's money down the drain.
Exactly. And you're paying for the instances in AWS, but you're not really using this instance. The second thing is that sometimes there could be raise when we boot up the node. We're hard in that part as well, but if the node fails to boot up, it won't even register to the master, which means if the autoscaling group in AWS has this node, but Kubernetes does not know it has one more node can use, or in that case, we're still wasting money, so we terminate that node.
So we orchestrate with the autoscaler to make sure that what the autoscaling group understands is sort of jives with what Kubernetes, what we see on Kubernetes.
We ensure everything should be consistent.
Right. And that's another thing that we are doing actually. So we are autoscaling our nodes up and down, right? So we have a cluster autoscaler that's running, and that's checking to see, okay, based on how much load there is on the system, we bring up and bring down nodes.
Right. Okay, so this is about the work we did to harden Kubernetes. There are some piece of summaries that you can keep in mind when you do tuning or you're working with your Kubernetes. First one is Kubernetes resource consumption is directly related to the number of pods cluster-wide and the degree of pod churns. If you have more pods, if you have higher pod churns, you definitely need to allocate Kubernetes with more resources to ensure the stability. And also you need to have a good estimation of what is the kind of workload your Kubernetes is supposed to handle. It is definitely good if you provision more resources to Kubernetes, but if you're over-provisioning things, you're wasting money basically. And that brings to my second point is that you need to find a balance among several factors: performance, stability, and last but not the least, the cost. So after doing all these hardenings, and Kubernetes is really stable and production ready for us. We run our Kubernetes to constantly deliver our end-to-end DevOps experience to us and our customers.
Awesome.
All right, so this concludes our Tech Talk today.
Thanks, guys. I had some questions that came in. So one, how long has your longest cluster been running?
I'll say more than half a year. We were during last year we're mostly hardening Kubernetes, and once that stage is done, our Kubernetes cluster has been running since then. I think it's more than 180 days.
Yes.
For our longest the development cluster. We upgraded our software a lot of times, but Kubernetes was still there, running heavily and safely to run our workloads.
Right. How often do you terminate your minions?
This is another good question.
So because of errors, I presume, right? So how often do we terminate our minions?
Yeah, exactly. So we do have a grace period to wait for our minions to come back once it is marked as not healthy or something goes wrong. we have a timeout. I think it's currently around 20 minutes. But if our minions don't recover within that timeout, which means like there can be even worse things happening on that minion, so we just terminate the minions.
Excellent. Any more questions? Feel free to ask.
And also we have some more details described in our blog series of making Kubernetes production ready. So if you're interested in, you can also go to our website to look at the blogs.
A couple more questions here. Hi, what storage driver would you advise for Docker when using with Kubernetes, specifically for CentOS 7.3?
Okay, great question. So we actually experimented with quite a few graph storage drivers. So we actually use Ubuntu on our system, so I cannot answer specifically for CentOS. We started off with using Device Mapper. We then moved to using AUFS, subsequently to Overlay, and then Overlay 2. So there are stories amongst each of them as to what did and did not work. Specifically, for example, Overlay had this like inode problem where you would still have space, but your inodes would run out. Yeah. And so Overlay 2 actually seemed to be the most stable. We've been running Overlay 2 for a long time. It is what Docker recommends as well. And so we've had pretty decent a run of luck with that.
And also, I think Kubernetes community has a bug opening for recommending the kernel and the Docker versions and the graph storage. I think they didn't mention specifically what kernel distros, but they do recommend kernel. Linux kernel 4.4 is something that they tested is relatively stable. No matter you're using Debian or Ubuntu or CentOS, kernel 4.4 is a good start. And Docker 1.12 is also a good thing to start with. But the entire community is still testing that. Hopefully we can get more updates from there.
Yeah, we are running 4.4 kernel. We are running 1.12.6, I believe.
1.12.6.
1.12.6 with Overlay 2.
By the way, this person Lakshman said he was using Device Mapper currently, and it didn't seem to be the best option. So that was
yes,
like we used that too.
Yes, we use Device Mapper, and definitely something we moved on from.
Okay.
Yeah, try Overlay 2, and this is what we are using, and we found it's so far so good.
Yeah. All right.
Yeah.
One more. How did you come up with the number 80 pods at M3.2x large nodes?
Good question. So Kubelet has a default of 110 pods per node, and actually we started with set default values. But we just realized that that number is too big. Sometimes it can make Kubelet stuck or Docker stuck. So 80 is something that we turn it down, and 80 is something that seems stable to us. So this is again the heuristics. Depends on the type of workload. So if you have a lot of containers, but they're not really taking a lot of resources, you're just sleeping or doing very light-weighted workload. So actually Docker and Kubelet will have more resources allocated to them. So it might be better. But in our case, 80 is just something we found it's good for us to start.
The kubelet is sharing resources with these containers on the nodes. So
exactly.
It does affect that.
Because the total number of, the amount of resources is limited on the node, so everybody shares the same pool of resources.
Okay.
That's the questions.
All right.
Awesome. Thank you very much.
Okay.
All right. Thank you
All right.
guys for your time, and we hope you'll join us next time and have a great day.
Done?
All right.
All right. Was it
Good job, Harry. All right. Thank you.